Swayam Prabha. Digital India. Educated India.
Welcome back. In module 11, we will learn about sewage treatment, and in lecture 51, we will cover introduction to sewage disposal and treatment in India. So, the different concepts that we will cover in this lecture will be basically on introduction to sewage disposal and treatment in the Indian context, then sewage characteristics, surface water classification as per water quality, then we will look into the general standards for discharge, then artificial methods of sewage treatment, biological sewage treatment, and then sewage treatment plants in general. So, when we talk about sewage disposal and treatment in the Indian context, as per news reports, because technically we did not find any reports on this, but roughly it could be estimated that over 60% of urban India's sewage enters water bodies untreated, roughly around 60%. So, as we know that, we have already learned that in most of Indian cities have got combined sewers, and so it is not, and also we have got most places in India receive a significant amount of rainfall, and so it is economically not viable to treat the entire volume of the sewage or the combined sewage that is generated. So, the system is designed in such a way, so that normally the sewage, when it comes from the different urban areas via the drains, both stormwater drains as well as the building drains, all of them connect to the combined sewer, and it comes to the point of disposal or an outfall, and there what we see that, or it could be even earlier. So, the sanitary sewage is the dry weather flow, the normal flow during the non-rainy season. In that case, that particular waste actually comes to over here, and then goes via this pipe to the wastewater treatment facility. So, wastewater treatment facility could be even in the urban area, so maybe the treatment is done over there itself. But when during the rainy season, the combined flow increases to an extent when it is too high to be treated, then the excess actually moves over, and then that is why we have provided a weir, jumping weir. We have already learnt about how jumping weirs are designed. So, that the excess flow actually, if this is the weir should be over here. So, the excess flow jumps over and then is disposed into the river. So, the normal flow falls onto this pipeline and goes to the sewage treatment plant, but as soon as there is excess flow, the excess volume jumps over and then could go into the to the outfall of the river directly. So, or in this case, after the water is treated, it could be reused, or it could be again disposed from the sewage treatment plant to the river as well. So, roughly this is the design in most Indian cities. So, we are not able to treat the entire volume of sewage. In most cases we dispose the sewage directly into the river, and roughly we can see that 60% of total sewage is not treated at all. So, the disposal point, as we have discussed earlier, is known as a outfall, and it is a discharge point of both treated as well as untreated sewage. So, both the treated and the untreated sewage comes over here, and usually it is comes via gravity conduit from the sewage treatment plant, or it could be a direct connection without the sewage treatment plant, where the connection is bypassed from the sewage treatment plant and it directly goes into the outfall, and or it could be a pumped conduit as well, because sometimes the outfall is much at a higher level because of the presence of levees and other embankments on the river. We have to actually lift the sewage and then drop it into the water body. So, that it could be a pumped conduit as well. So, usually because it's an outfall, we would try to maintain that the invert level of this particular conduit is at least 0.5 meter above the mean flood level of the receiving water body. So that is what we would, so that there is no backflow. So even though we have learnt about backflow prevention devices and all this, but this is the standard norm that it should be above the general flood level of that particular water body. So usually the discharge is first let into a receiving well from where it spills over to the river or the water body. So that means always there is a storage, so that in case of a device for this backflow prevention device, that means when it is stopped, whatever sewage comes in, that has to be accumulated and stored for a certain point of time. So there usually is a receiving well from where it spills over to the river. So some amount of storage is provided at the outfall as well, sometimes, not always. So in this particular lecture, we will look into the broad two aspects of the ways in which we treat sewage. One is the natural method, under which there is dilution and land treatment, which we will learn in details in a later lecture. And then there are artificial methods, which also include primary and secondary treatment, which also we will cover in subsequent lectures. But first of all, we need to understand when to provide artificial natural method, when to adopt a natural method, when to adopt an artificial method, and not only that, what are the standards of discharge. That means once the sewage is treated, how much amount of treatment has to be given to it, and it again depends on the characteristics of the waste. So all these things plays a role in determining what kind of sewage treatment we will provide in a particular scenario or a particular context. So in this table, you can see the contribution of human waste in terms of grams per capita per day. So you can see that the human waste includes both this BOD. So the biological oxygen demand from human waste comes to around 45 to 54 grams per capita per day. Similarly, total solids comes to around 170 to 220 grams, suspended solids 70 to 145 grams. And then you have got ammonia, you have got nitrogen, you have got chlorides, you have got phosphorus, all these things. Some of this we have learnt earlier, that whenever we were thinking about creation of biogas, mixing both human waste as well as cattle waste. In that case also, we are talking about that human waste is rich in certain nutrients which could be used as manures, and at the same time we can also create some form of energy from the gas that is generated as well. So we have already learned some of this earlier, but you have to understand that this is the kind of loading that goes into the sewage. That means this is a kind of waste, the different components of the waste that is there in sewage, and based on that we can also determine what sort of treatment is required. But sewage is not only the human waste, it includes waste from kitchen, because we are going for combined sewage. In most cases, Indian cities have combined sewage. So sewage actually includes waste from kitchen, bathing, laundry, urine, night soil, and all of this is either in dissolved state or colloidal state or suspended state. We have already learnt about these different states. In addition to this, there are also different kinds of salts, which mainly comes from cooking, from human sweat, then bathing, then laundry, and then also from urine. And then in addition to that, we also this sewage also includes pathogen from night soil. So that means we have to make provision for treatment of pathogens. We have to make provision so that some of these salts are removed, and we have to also make provisions that the basic dissolved colloidal and suspended waste has to be removed from the waste. So raw sewage, the pH value, as you know that the pH value influences different processes. That means different chemical reactions, different processes are influenced by the level of acidity or what kind of in that particular sewage. So usually raw sewage, we find that the value comes to around 6.8 to 8 is the pH of raw sewage. And ammonia is the major fraction in terms of nitrogen. You see that we have got total nitrogen, organic nitrogen, free nitrogen, ammonia, nitrate. So there are different nitrogen components in this waste, but ammonia is the major fraction of total nitrogen in domestic sewage. and BOD of sewage varies also from place to place. Now, why this BOD varies? Because two things when we design a sewage treatment plant, we consider the organic loading, that means the BOD that we have to remove, the BOD loading, as well as the total suspended solids or total solids in that particular sewage. So, these are the two components that we have to remove. So, while primary treatment reduces the total TSS, the total amount of this total solids, whereas this secondary treatment is primarily devised to remove the BOD from the waste. So, that is and that means we also need to understand how much BOD we have to remove. So, if you remember from one of our earlier lectures, we did calculate that if we add more amount of sludge from this septic tank into the sewage treatment plant, how does it affect the BOD loading of that plant, and is that plant able to reduce that amount of BOD. So, that means every plant is designed to remove certain amount of BOD, certain amount of this total solids. So, BOD or the raw, or you can say that the raw sewage characteristics is not the same. In different areas it varies, and it depends on the level of water supply, that is the concentration. If the concentration water is less, then it will have a different concentration, and per capita pollution load. Then settlement and decomposition in sewers depend on the designs of the sewers, depends on the age of the sewers. If already a lot of settlement and decomposition is happening there, then it does affect the BOD content as well as the total solid content. Then partially decomposed sewage from septic tanks, if we are adding them or not. Then lifestyle of the people who lives in that particular area, that means the economic profile, all these things plays a role in determining the type of characteristics that the sewage for that particular area will have. So, the sampling strategy for sewage over here is, it should be we should be able to consider the diurnal variation throughout a day, the variation in the flow of sewage, and usually we take 3 samples per month, 2 from weekdays and 1 from a Sunday, to determine what is the sewage characteristics, if there is some change, or and accordingly we can readjust the kind of treatment process that we actually or the existing processes in the sewage treatment plant, we can change some certain parameters based on our surveys. So, now as you know that we analyzed water quality of a particular area. I said that when we go for certain development plan exercises or maybe for some planning exercises, we sometimes need to carry kits with us to treat water and to see what's quality, is it potable or not, and so on, right. So, this is something similar, where as you know that sewage samples could be analyzed for pH, temperature, color, odor, alkalinity, TSS, volatile, suspended solids, BOD, COD, nitrogen. So, then there is ammonia, then there is TKN, which is total Geldal nitrogen and NO nitrates, phosphorus, total coliform and fecal coliform, TDS, chloride, sulfates, heavy metals, and so on. So, these are the different things that we can test to determine what is the quality of sewage, and and similar test has been done for water quality as well, and basically sewage is also water. So, it is 99.9% water. So, in that case also you can actually test the quality and determine what is the quality of this particular water, or in this case sewage, of course. So, now if you go to the field, like for example, when you go to conduct a survey, then you can test the surface water sources during field survey, and you can determine if they are suitable for certain purposes. That means, if not, then we have to propose certain remedy measures. So, you go to urban area, you survey the different water bodies or the lakes and all, and you have to give proposals like should there be any type of projects which will actually look into prevention of sewage inlet into those particular this water bodies, or there would be a project so that there will be some form of treatment before the water that overflows from the surrounding area goes into this particular water body, or should there be a drain around so that we can divert this particular runoff that goes into the water body, or is there a need for connecting multiple water bodies, right? So, all these things needs to be tested. So, for that we can test the water quality, and based on this particular standards that are given over here, where you can see that if you want to see if the water is suitable for drinking and without conventional treatment, but maybe just after disinfection, then probably your pH value of the water has to be within 6.5 to 8.5, DO levels has to be 6, and BOD value 6 or more, BOD value has to be less than 2, and total coliform or MPN this should be 50 or less. Similarly, for outdoor bathing, if you want to classify that, okay, these are the water bodies suitable for bathing, you need to check the same parameters, and you have to see the values which are conform, if it is conforming to this sort of values or not. Same goes for if the water body is suitable for propagation of wildlife and fisheries, is it suitable for wildlife or fisheries, or if it could be used as a drinking water source with certain amount of conventional treatment followed by disinfection, or is it good for irrigation or industrial cooling. So, we can actually check these particular values. In case of because we are using it for industrial cooling, maybe electrical conductivity could be also checked, and the value should be less than 2250 micro ohms per centimeter. Sodium absorption rate as well is also checked, boron values are checked, and so on. So, these are the different checks that we can do in the field, or like similar water quality test, we can also test the sewage quality and determine if this particular water body is suitable for certain purpose or not. So, this table actually shows the general standards for discharge of environmental pollutants part A as per effluents as per schedule 6 of the Environmental Protection Rules of 1986 and the National River Conservation Directorate guidelines for fecal coliforms, values in milligrams per liter unless stated. So, this gives you the entire list of the total once you treat the water and you let the water out for maybe disposal. This is the standards for discharge of environmental pollutants. So, that means you should make sure that after treatment the sewage reaches this particular quality. For example, the color and odor should be of order B. B is what? B is all efforts to remove color and unpleasant odor. Suspended solids values should be 100 for inland surface water, for public sewers 600, land for if it is released in land it should be 200, and marine coastal area C and D. So, C and D is again 100, and if it is used in cooling water effluents then 10% above influent. Then pH value should be around 5.5 to 9. Particle size, temperature is H. H is shall not exceed 5 degrees centigrade above the receiving water temperature. Then free ammonia value is 5. Then arsenic values are given as 0.2, mercury, lead, and all the different values are being stated. That means, after treatment we should be able to reach this kind of values after treatment, and if not, then probably we have to look for other treatment measures, or we have to look for other ways to actually treat the sewage further. So, these are the general standards of discharge. You can actually know that these are the standards, and again you have to match it whenever you do your testing. You have to match with this particular standards if your discharge actually adheres to these rules or these guidelines, right. Then what sort of treatment we should provide, and what kind of treatment is able to be achieved by that kind of particular technology or that kind of technique. So, for example, when we look into the different artificial methods of sewage treatment, it includes both primary treatment as well as secondary or biological treatment, and then final treatment is also there. So, usually we start with primary treatment. We will detail it out in later in the next lectures. So, first we start with primary treatment, and once primary treatment is covered, we are able to reduce the suspended solid load of the sewage. That means, we through sedimentation or sedimentation via coagulation, then removal of grit, and all these things we will do so that suspended solid load is reduced. And then we do secondary or biological treatment, where microorganisms, both aerobic and anaerobic organisms, act upon the particular sewage media, and then using several kinds of techniques we can actually remove the BOD for that particular sewage. So, this is then the final treatment could be, again we do some amount of filtration, we do disinfection, we can again put the sewage to certain filters so that we remove particular material, right, particular metals and so on, and so and particular minerals and so on. And so, this is the three artificial treatments that are there, or the three stages of artificial treatment. And as you can see in this particular table, you can see that what amount of treatment is possible. For example, screens are there which reduces suspended solids by 5 to 20, and then this is percentage removal, bacteria by 10 to 20% and BOD by 5 to 10%. So, then plain sedimentation tank, which is a primary treatment, almost 65% of suspended solid reduction, 70% of bacteria reduction maximum of course, and then only 40% of BOD removal. So, see, in the plain sedimentation and sedimentation with chemicals, we can again reduce the suspended solids up to 90%, 80% of bacteria removal, and maybe 50 to 85% of BOD removal. So, these three are the primary treatment, right. Whereas, for the other secondary or biological treatments, we will learn again in details about these processes in the subsequent lectures, but this is one process which is known as a trickling filter, and low rate trickling filter followed by sedimentation. So, see here we can achieve around 95% BOD removal, right, and high rate trickling filter followed and preceded by sedimentation. So, we do sedimentation before and also do sedimentation after. Now, and in between we use this high rate trickling filter. So, here also we can see around 95% removal and also 92% removal of suspended solids, because we are doing both the sedimentation as well as the trickling filter together. So, that means both primary and secondary treatment together, right. Similar to trickling filter, there are other set of processes which are based on activated sludge process. That means where we mix the sludge back into the incoming waste water, so that we introduce the bacteria in the sludge for the treatment, right. So, again we will elaborate this later on, and you can see that over here we can remove around 98% of bacteria, 90% of solids and 96% of BOD as well. So, in this way we can see the different processes, and then I think this sedimentation is not the plain sedimentation. This sedimentation is the final sedimentation after all the treatment, and this intermittent sand filtration is another form of this biological treatment, and here you can see that the bacteria and the BOD is removed, and finally at chlorination is targeted towards removal of bacteria or pathogens, and so this we can see that the 99.2% of BOD is removed, there is no bacteria at all in the sewage, right. So, after this particular addition of chlorine. So, let us look into so these are the different artificial treatments that we are talking about, and within artificial treatment we also have got biological sewage treatment. And as you know that in biological sewage treatment, biological organisms are allowed to consume the organic matter. So, that means biological organisms act upon the sewage, and the organism secretes some enzymes which dissolve the organic matter, and this is actually the food for the biological organisms. So, this particular organic matter, and once they get food, they will grow and multiply, and then they basically will further consume more amount of this particular waste, till there is no waste to consume, there is no further organic matter to consume, and once that consumption is done, that means there is no food, and also because of the use of oxygen, this bacteria will actually die off. So, at one end we are reducing the organic loading, that means we are reducing the BOD, as well as the bacteria itself would be removed at the end of the treatment process. So, you can see in the two processes that we have already talked about in earlier lectures, one is the aerobic process which requires oxygen, and then there is the anaerobic process which also requires oxygen, but the oxygen is not from environmental oxygen. The oxygen molecules are taken from that particular compound itself, right. So, that means anaerobic process happens in absence of oxygen, but it requires oxygen which is taken away by breaking this particular complex organic matter, and we take the oxygen from that matter. So, the reactions in the first one and the second one are different. So, the output of the outcome of the reactions are also different. So, we have suspended organic matter, and once it is mixed with water. So, we have hydrolysis, which is when certain chemicals break down because of mixing with water, and then we get soluble organic matter. This is acted upon by residual biodegradable organic, and we also have got residual biodegradable organic matter in that particular sewage. So, this entire thing could be now acted upon by this microbial biomass, and due to that we can have bioreduction, which leads to, and also in the presence of oxygen, that will lead to CO2 production, H2O production, ammonia production, and of course heat energy production, right. At the same time, because of the food from the organic matter, this along with the residual biomass, we also have new heterotrophic microbial biomass. New biomass is created, new microbes are created, and these are again acted upon by the oxygen, and we have auto-oxidation, which leads to, again this breaks down into CO2, H2O, NH3 energy, and so on. So, more or less both the bacteria is acted upon as well as the organic matter is acted upon to release this kind of gases and water, CO2, ammonia, energy, and so on. Now, then this is the aerobic process, and ammonia gets converted into nitrates, and this carbonaceous BOD is the sum of the oxygen utilized during biooxidation of the organic matter and during auto-oxidation of the microbial biomass. And similar to aerobic process, the anaerobic process, the difference is everything else more or less remains same. The reaction that happens that leads to formation of methane, H2O, H2S, NH3, and energy. So, instead of CO2 we are getting CH4, which is methane, and also we are producing H2S gas. So, that is why in anaerobic conditions, if anaerobic conditions persist in a particular area, that means there is not oxygen, the decomposition is happening via anaerobic process, then it leads to some bad odor, which is primarily because of this H2S gas, and it also releases CH4 or methane. So, this is basically the two biological processes that we will that is actually employed in any sewage treatment plant as well, or these are the natural processes of decomposition, one in presence of oxygen and one in absence of oxygen. Then we will talk about the sewage treatment plant. As planners, urban planners would always like to reserve certain area for sewage treatment plant. Two things: they will first like to understand that what is the water quality, what sort of treatment is required, is the water going to be reused, then again the treatment quality has to be changed, and how much volume of water has to be treated. Based on that, we can determine that what sort of units should be there and what would be the size of those particular units of treatment units, and then we can determine the size of a plant. But general rule of thumbs are there, but actually it is very, very difficult to say that exactly so much amount of land area has to be reserved. And also not only the amount of land area, but also location for it, right. So, a location of STP is determined by analyzing the contours of that area. Elevations and soil tests are conducted initially, and once we know that, then we also check the rainfall data for 50 years and highest intensity rainfall during that period, which will give us the total quantity of runoff generated in that particular area, which gives us an idea about the flooding potential of that particular area. Because in case of sewage treatment plant, because we are dealing with sewage, we have to be very, very careful about flooding. If the area floods, then automatically we can assume that the entire sewage that comes over there will be mixed with this particular water, and particularly if we have got stabilization ponds or large scale basins where we put in the sewage, or maybe sludge drying tanks, all these things will get inundated, and that will lead to contamination in that particular entire area, right. So, that is why we should be very, very careful about flooding when we set up a sewage treatment plant. We should also look into the earthquake records, and maximum flood level at the site, and in the receiving water body wherever we are putting in the sewage. We would look into the windrows, because sometimes there is smell from odor from the sewage treatment plants, which also needs to be controlled. So, in many cases we find that the cost of land in an, because sewage treatment plants has to be set in an urban area, and so particularly in case we want to reuse the water, that means we should have the sewage treatment plant within the urban area, so that after reuse we can again send back the water. If we have the sewage treatment plant far away, then automatically that means the sewage will first go there and again return from that plant. So, there is unnecessarily we have to lay pipelines, and it will increase cost, right, and energy as well, because pumping energy is also would be spent. So, better to have the sewage treatment plant in the urban area itself, right. So, because it is an urban area, we find that in many cases the cost of land sometimes exceed the cost of the STP itself, right. So, that is understood. That means that all the different the costing, we have to be careful about that part. And also how much amount of land area is reserved, it says as per thumb rules around 0.2 to 1 hectare per million liters per day of sewage treated, but also as per the technology adopted. So, in case waste stabilization ponds are used, then we require a huge amount of area, right, because these are natural basins where waste is put there for a certain amount of time and automatically acted upon by the natural elements and all. And so, waste stabilization ponds require a lot of energy, but if we go for more artificial treatments, and then we do not require that much amount of space, but at the same time this 0.2 to 1 hectare per MLD, this is a very broad rule, and this will vary as per the technology adopted for this particular treatment. So, as we go and discuss about the different technologies, we will also discuss about the space requirement and so on. So, in addition to all this, we should have reserve area for the sewage treatment plant to grow in future, and also we need to have buffer zones around the sewage treatment plant. So, around 100 meter from the odor producing units to habitation, if deodorization systems are not provided. So, if deodorization systems are provided, then we can reduce this particular distance. Otherwise, we should maintain at least this 100 meter of distance between residential areas as well as a sewage treatment plant. And a sewage treatment plant is usually will find that proper grading and landscaping has to be done, and roads has to be at least 20 centimeter above the finished ground level. Stormwater drains has to be there on both sides, so that we have to prevent flooding in this particular area. Then it is preferable to take cables and pipelines between the treatment units underground, and through RCC walk through box culverts connecting the units below ground level. So, that is how we should connect the different units, right. So, this actually this actual figure is provided in this CPHEO manual, and this is land area required for STP as per the different technologies, but you have to understand that many of these technologies are provided in combination. It is not like just one thing would be added. For example, you see TF, that is trickling filter. Trickling filter is not just there alone, right. So, the space required by trickling filter is something around here. So, what it means is a sewage treatment plant including trickling filter will probably require around 2500 square meter of area per million liter per day of sewage that comes into this particular plant. Similarly, you see that this waste stabilization ponds, if it is lined or unlined, or in that particular case the area required would be the maximum, which comes to around this maybe 23,000 square meters of area per MLD of sewage treated, right. Similarly, we have got so many different processes. You can see these are the secondary or biological treatment processes which could be adopted, like activated starch process, sequential batch reactor, moving bed bioreactor, or fluidized aerobic bioreactors, membrane bioreactors, then BioFOR, biological filtration and oxygenated reactor, high rate activated sludge, BioFOR F technology, and so on. So, there are so many technologies, and primarily these are different variations of the basic theme, that is either it is an activated sludge process or it is a sort of a filter process, right, where certain media is used, and then we add air or we add, or we actually make the media in a fluidized state, like the media or this filter media like sand, or this this the brick beds through which the sewage passes, and we made them of plastic, and then they float in that particular sewage media, so it becomes fluidized. So there are so many processes that could be adopted for biological treatment of sewage, and as you can see, some of them are listed over here, but in addition to this there are so many more. So we can see that these are the area required in different cases, like we have got a SBR, and then dual media filtration. So if this kind of combination is given, this is the space required. You see that requires very little space, right? Membrane bioreactors, I think it's something around over here. This requires the least amount of space. So we will learn about these technologies in the subsequent lectures, how this actually operates. So you have to understand that each of these technologies are different. They are able to treat or the quality of discharge that you get out of using these technologies are different, and the next is the space required for these technologies are different. The costing and the operation process are different. So you need to have an understanding of all this, at least the fundamentals of these technologies, to take a call on what should be provided in a particular area or in a particular context. And whenever you are making a decision for the people, that means for an urban area, you need to actually take the feedback of the people, right? That what amount of money they are willing to pay for this particular technology. And then you also need to evaluate the pros and cons of each of these technologies, right? So until unless you understand the basic processes, until unless you understand the costing or the space requirement and all the different other parameters that goes for this particular processes, it is very difficult to take a decision. So to take this kind of decisions by a decision maker, so we need to understand this kind of all these different technologies which are available for us to adopt. So two examples, you can see that this is a sewage treatment plant, and the design actually, this particular image is from 17.5 MLD STP at Indira Gandhi International Airport in Delhi. Why this is given? You can see there is an anoxic tank, aeration tank, and a clarifier placed together. Now, what is the purpose of clarifier? We already know clarifiers because they scrape the sludge that happens during sedimentation and brings it to a point. We have learned that in water treatment, right? Aeration, we add oxygen, right? Anoxic tank, this is where in absence of oxygen, this nitrification happens, right? So that means this is certain process which happens in the absence of oxygen, and this is where also this ammonia is acted upon, right? So all these processes are actually combined together in one plant. So we can have several techniques combined by designing a plant which is actually a combination of all these techniques. So we provide different chambers for all these techniques, but all of them combined together. So definitely the area and the cost of construction can be significantly reduced by integrating multiple sewage processing units. And if these are rectangular or square tanks, they can be just side by side with the sewage moving from one tank to another. And if they are circular tanks, they can be placed even concentrically. So for this, in this particular example of this Indira Gandhi International Airport, you can see we have the anoxic tank at the beginning. This is the mixture, and then once that means we have got raw sewage, and then so once that is done, then this nitrification starts happening, and this water actually passes through this particular pathway. It goes like this, it goes round and again turns. So this is where you can see that this is where the water is moving, and then this is the once it comes to the center, then this is the clarifier where all the sludge is actually gathered, and then we are getting rid of that. So we can do aeration along this process as well. So these are the aeration tanks, the in between is the settling tank, and then at the beginning is the anoxic tank. So all these different tanks are put together and we get a overall compact treatment unit, right? So this is how we can also reduce space in by combining this. But again, these are very much engineering design. So as decision makers, you don't need to have detail. You don't need to create this sort of designs, of course, but there are several available designs, but you need to think of that if you can choose something like this to reduce the area requirement and so on. So, similar to that, we can also use, we can avoid buried valves to make the operation more easier. We can use for operating stop gates, we can use hand wheels on a rack and pinion to reduce cost as well. So, these are different options that are available, using which you can reduce cost or reduce space and so on. So, let us look into another very important case study, a very interesting case study. This is a 200 MLD STP in Nagpur, where we are actually treating the wastewater as well as reusing it, and this was developed on PPP basis, and this plant actually led to savings of 190 million liters of fresh water per day. That means we are able to reuse water and we are reducing the fresh water requirement by 190 million liters. Now, why this project is interesting, I will explain. So, this project is made by Nagpur Municipal Corporation, and the companies or the PPP model was implemented via this Vishwaraj Infrastructure and two partner companies who formed a special purpose vehicle. And this this private partner actually invested around 236 crores for construction cost, right, and they were also responsible for operation and maintenance as well. And the payment has to be made by this Nagpur Municipal Corporation, and this revenue, that means that this is the revenue that the private consortium earns, and that comes to around 32 crores per annum for 30-year period, right. So, this is the money the municipality keeps on paying the company for keeping this plant operating. So, this is the image of the plant. You can see from the top, the plant is set up in Bhandalwadi near an existing 100 MLD STP on a 6-acre site. It takes 50, so where does it get its water, wastewater? It takes 50 MLD of water from the Nag river and 75 MLD water from the Pivali and Pohara river each. So, altogether you can add up 75 plus 75, 150 plus 50, around 200 MLD of water it takes up, right. So, this 200 MLD. So, why it takes water from the river? Because these rivers are called rivers, but actually these are sort of canals where wastewater is dumped from the entire Nagpur, and all these rivers receive all the sewage from Nagpur, and basically it is a sewage stream, you can say. So, it takes up the water, it cleans it and again puts it back. So, now this contract has an option to sell the treated water with revenue share with Nagpur Municipal Corporation. So, that means they are able to sell, if the water is reused, then the money that would be generated by selling it has to be shared with NMC. So, out of the treated water, that is 200 MLD of water is treated, and 190 MLD of treated water is sold to power plants at Koradi and Kharpar Keda. So, that is in the first one takes around 90 MLD of water, and this the next one takes around 100 MLD of water, and both these thermal power plants are run by Mahagenco, right. So, this is a arrangement where the thermal power plants are taking the water that has been treated, or this water is reused in the thermal power plants. Now, how is that possible? This is because power plants within 50 kilometers of STP are mandated by law to use treated wastewater. So, you can see that this is a very, very nice project where the reuse, the feasibility of treating the water is possible, because there is a reuse, a provision for reuse which is mandated by law by these thermal power plants. So, that is why this treatment actually is profitable, and that is why a PPP model could be set up for this kind of treatment process. So, the construction time for this project was 15 months. So, you can understand that this sort of projects, if viable, could be set up in other parts of the country as well. So, to conclude, surface water sources can be tested during field survey to determine the suitability for use. Area required for a STP depends on volume of wastewater or sewage treated and the technology or combination of technology used. Effluent discharge should follow the general standards for discharge of environmental pollutants rules, and the PPP model can be viable for STP projects provided there is effective reuse of treated wastewater. So, these are the references you can study. Thank you.